Hi there. So we're going to start talking today about measures of central tendency and how we summarize data in education. We're also going to be spending some time talking about variability, standard deviation, converting scores. Let's see, what else? We're going to be talking about mean, median, mode, and range, and different ways of actually visualizing information with charts and graphs. So we have a lot of things to take into consideration, and I understand that coming into this, some of you may have more or less knowledge on the subject. To be in sort of a fair, I have to assume that there is no knowledge going into this really about the different terms and how you calculate them. And so if you are familiar, please just make sure that your understanding of a term is on par with my own, in which case you'll be fine when the exam rolls around, and also in applying it for future projects down the line. If not, then please do pay attention along the way and take notes on the PowerPoints that were published to the Blackboard page. All right, so as you can see, we're going to be talking about a lot of different things. I have made a second presentation with percentiles. That's going to be posted separately just because this is going to be a huge video covering all this information. So let's get going. All right, so when we talk about statistics, we're generally talking about two different types of statistics. We're talking about descriptive things, and we're talking about inferential statistics. In this class, we are not talking about inferential statistics, which is frequently what you think of when you think about like a course of statistics. Those are generally going to be inferential statistics, whereas the descriptive statistics, which we are talking about, are how you would go about describing a data set. So if I have, my students' exit scores, then I might be able to describe them as a group. So that is more what we're focused on in classroom assessment. Okay, so this is an example of a frequency distribution. In this, you can see that we have our scores listed. They are going from high to low, and then you can see next to scores frequency. You can see that there was one score of 40, one score of 35, 3 scores of 34. Then we have cumulative frequency, where we start adding them up from low to high. And then we look at percentile and percentile rank. So we're going to be talking about percentiles and percentile rank in the other video, so please stay tuned for a better understanding of just how it is you calculate percentiles and what they mean. But I want you to know that this is what a frequency distribution looks like when you are writing out all the scores. Okay, so this is a bar graph or a histogram. We generally refer to them as histograms, but in general, these are things, this is for data that's non-continuous. So when you can't break something up, like I can't break Hunter into multiple pieces of Hunter. Hunter being a student, like you can't break them up into pieces. It doesn't work like that. So this individual student has read this many number of books. That is how you would plot or draw a histogram bar chart. So in this, you try to make separate categories, and then you're plotting then how many of something each person or each thing has done. So it is also a measure of frequency. Okay, so when we start looking at frequency polygons, this is where we start getting a little more interesting. This is for continuous data, so and this can be expressed as a fraction. And you sometimes have test scores that are grouped like this, and then they show frequency distributions. We're going to be seeing a few more of those as we get further into the course. But in general, here you can actually do and connect lines, because there are heights that range from 160 to 170. They're not isolated events. So this is a combination, and that's in general just to represent that you can make combinations of these things. So our histogram and our frequency graphs going together to sort of merge and to become not as isolated. And in that, you generally are having a value on the x-axis, and on the y-axis you're counting up. And let's see, what else do I want to say about this? It's not as common as you might think. We don't generally see histogram frequency polygons like that. That doesn't come up that often. You're generally looking at bar charts or correlations or something of that mag. All right, so when we start talking about distributions, we're very interested in how things are grouped together. And I wonder, have you heard of a distribution before? So distributions are generally describing patterns, and some of the most common patterns are bimodal distributions and unitary distributions. So bimodal means that you've got sort of like two humps that are occurring in your data set. So if you contextualize this to a classroom, you could have a group of students that are performing very well and a group of students that are performing rather poorly. And then in the middle, which is going to be the very sort of low point in the middle, right sort of above or unitary, you're going to have fewer students that are doing like a mediocre. And that's not to say that we're characterizing students at all, just that the data happens to be falling that way for that particular test. And I want to make a note that on the right, you see the unitary distribution. If you'll notice, they are not all level. So even though it's uni, as in like all one height, they can be sort of deviations of that height. They aren't have to be exactly that height, but there can't be any obvious pattern to the differences in the distribution. So when we talk about distributions, we generally think of a normal distribution, which we're going to talk about in-depthly very soon. But in general, we talk about these sort of smooth curves that have sort of a bell-shaped aspect to them. And we sort of imagine that in our histogram that we're looking at a bell. And that I'm going to show you a picture where this makes more sense very soon, but the idea that the 95% of the bell is just wide enough that you can fit 4 standard deviations in it. And that's going to make a lot of sense in the near future when I show you the normal distribution in its full glory, as it were. But in general, this sort of smoothing out of the way the distribution works allows us to make predictions that are theoretically appropriate for the underlying population. And I say theoretically appropriate because you can run into issues like we did with the FSA, where you test on a group of subjects that are not your population of interest. And then you start creating normalized means for that population that took the test. But if that isn't who the test is meant for, then you start running into problems with interpretation. Okay, so this is an example. In the very middle, we have the mean, and that is 68 inches, or 5 feet 8 inches, with a standard deviation of 4 inches, which means that on either side, so plus 4 inches and minus 4 inches, we're going to have a standard deviation marker. And this is just for height. So this is then saying that, let's see, 68 inches has a frequency of, I would assume that's for like 25 maybe? Anyways, the idea here is that you have this sort of bell smooth aspect to it. So you can sort of see that on either side of the dotted line that you have a mostly equal distribution on both sides, and that's what we would consider normal. Not that it is perfect by any means, but that it is more one hump than two. So if you remember back for a second, we had that bimodal distributions where there were clearly two sort of mounds that were occurring. So if it's not two mounds and it's not flat, then it is generally normal. So this is leading us into, well, what does the real pretty picture look like? And that's on the next slide. All right, so here's our nice pretty picture. This is the bell curve, the standard normal distribution, and this is something that you should become very familiar with. I have uploaded the image of this bell curve for your own printing capabilities on the website. And when we start looking at this, we start teasing it apart because there's a lot going on in this picture. So straight in the middle, you have this 0. So that is assuming that your mean is 0, right? And so anything to the left and to the right of this 0 are going in the direction of, to the left, negative standard deviation, and to the right, positive standard deviation. And you'll notice that parts of this curve have been broken into smaller segments. So you've got this 19.1%, the 15.0%, 9.2, 4.4, 1.7. And that's going to become really important soon as we start grouping these together and making sort of rules for ourselves about explaining what's under what section of the curve. But what I want you to take away from this is that to the left of 0, you start talking about negative standard deviation. So you have -1 with a sort of 0 with like a cursive O almost, and then -2, -3, -4, and these are 1, 2, 3, 4 standard deviations away from the mean. And that's important because that's supposedly the entire population being explained by this curve. And then because this curve is assumed to be normal, we can make a lot of other assumptions about it. And we start getting into those assumptions when we start talking about cumulative percents. And we're going to talk more about that in percentiles and also when we talk about converted scores. So I will wait to go into that until a little later on. All right, so when we talk about the symmetric distribution, we mean that the mean, the median, and the mode are practically on top of each other, so much so that they can be assumed to be the same. And we're going to go into that in detail for each measure of central tendency. So the mean, the median, and mode, we're going to talk about all three. But in general, you can assume that if you're talking about a standard normal distribution, that all three are very close together. Okay, so when you talk about the most scores in the middle, you're assuming that they're within one standard deviation. And we're talking about standard deviation later, but in general, we're talking about demarcation lines between sort of artificial constructs. And so I think that this is an important thing to remember. And I know it's kind of an odd placement for it, but I don't have anywhere else better to place it. But I want you to remember that even though you're seeing those theoretical lines on the page about where the bell curve breaks percentage-wise, that the difference between a 92 and a 93 is 1 point, and that it's more of an arbitrary cutoff that we have decided upon than it is an actual understanding of ability. So it's something to keep in mind that even though we are talking about these standard deviations, that they are not the end-all and be-all of the real world. So please do keep that in mind, that not everything really needs to be decided with a test score, but rather sometimes you need to really consider what's best for the student and the student's abilities outside of test taking. All right, I will get off the soapbox now. All right, so when we start looking at the standard normal curve again, you'll see that we have the mean score in the middle. Remember, to the left, negative standard deviation, to the right, a positive standard deviation. And we'll start saying that in that -1 standard deviation, we are explaining 34%. To the right, 34% should be in there as well. 14% should be between 1 and 2 standard deviations, and beyond 2 standard deviations where there should be about 2% of your sample in that is under the curve for that section. So when we start thinking about how to actually conceptually talk about that, well, if you're at the mean, you scored average, right? You scored just about the same as everyone else. And that's sort of what's going on between -1 and 1 standard deviation away from the mean. You scored just about the same. One more standard deviation out, so between 1 and 2 standard deviations, you are doing better and worse than others. And +3 and -3 standard deviations away from the mean, you're doing significantly, well, I say significantly, you're doing like appreciably worse and better. I would say be careful if you happen to use the word significantly, because that has a connotation that is very specific to the world of statistics, where you're not proving, but you're attempting to test something, and it's showing that 95.5% of the time this is true. But that is not the sort of idea that you're trying to express here. So don't let that slip out like it just did for me. Don't say significantly if you can avoid it. Okay. All right, so back to this normal distribution stuff. We are, again, talking about proximity to the mean, and this is saying that 68.26% of scores will be ±1 standard deviation away from the mean. 95.44% will be within 2, 99.84 will be within 3. And that becomes really important because we can break that down further. Oh, okay. So are these two distributions the same? Your answer should be yes, they are. They are telling you the same thing, because within 1 standard deviation of the mean, 68% is 34% on one side, 34% on the other side, to sum to 68%. And so when we start thinking about this 95%, we're saying, okay, it's that 13.5, that 34, and that 13.5 again, all added up to get that 95. And then the same with the 99, you add everything together. So yes, those two distributions are expressing the same idea, even though they're laid out a little differently. Okay, so now we're going to talk about skew, which is a very interesting concept, because when we think of skew, we generally think about this a little backwards. So, okay, so this is the positively skewed distribution, and I want you to take a look at the way this graph is looking. So when we think about this, we generally, in education at least, plot it on a test score lines of 0 to 100. So 0 being this first bar on the left, and 100 being the last bar on the right, in which case that's not a very good sign for your class if the majority of scores are on the 0 to 50 side of things. That's generally not considered a good thing. And I think that one way to think about this specifically is that you are looking at sort of the reverse of what you're generally thinking for education. We'll just say it like that. So a positively skewed distribution is not something you want in your classroom. That's bad for normal test scores. It's good for like disorder diagnosis in medicine, but it's not good for your classroom at all. And I'd like you to take note for a second that this is an asymmetric distribution. And we say that term asymmetric because even though this is sort of one hump, one grouping of bar charts that you're seeing, it's not perfectly symmetrical. So if you remember, if our bell curve was, a very specific bell shape, this, which we would call symmetric, where both sides are the same, like if I folded it in half, I'd get the same shape, I would not get that here. And that's what makes it skewed. Okay, so now you're taking a look at a negatively skewed distribution. And again, this is a little different than what we would normally think it would be. And in fact, you want a negatively skewed distribution in your classroom, generally. That means that on the far left, you're looking at 0, and on the far right, you're looking at 100. So the majority of your students are doing very well on whatever test or quiz or whatever it is you're giving them. That's what you want. You want a negatively skewed distribution. But again, this is an asymmetric distribution because if I was to fold it in the center, I would not have the same shape on either side. It is clearly more on the right than it is on the left side, which again makes it negatively skewed. Okay, so this is the positive and negative skewed, and you're also being able to see negative skew, normal skew, and its impact on mean, median, and mode. So again, negatively skewed, you're going in the negative direction. Positively skewed is headed in the positive direction, and that's in the sense of not test scores that they're talking about. So what they mean is that your mode is going to be more important when you're skewed, and the median is going to be a better approximation of the mean or the middle of the distribution when it's skewed. So if you can see in A how the mean is not anywhere really near where the center of this distribution is, that is the impact of skew on a distribution, in which case sometimes the mean, the average, is not the best way of explaining what's going on with the distribution. Same thing is happening in C, which is the positively skewed distribution, where your mean is, in the center here, but it's not really the center. The mode is the center, and the median is close to the center as well. And I want you to then remember that in a perfect distribution, the mean, median, mode are practically on top of each other. So this is sort of showing the impact of what different types of test scores can do to your statistics that you're going to calculate. So it's definitely something to keep in mind about when you're considering the measures of central tendency. Okay. Speaking of, here are some measures of central tendency. All right, so we have the mean, which is our average, the median, which is the middle, and the mode, which is the one that is occurring the most often. And they're not isolated particularly, but I'm going to go through them one by one. In this particular graph that you're looking at the mean, and you're looking at the median and the mode. And in this particular graph, you're looking at a skewed distribution. Do you know which way it's skewed? I'll give you a second to answer. It's positively skewed. And so that means that the mode is showing you the best approximation of the truth for your distribution. So if 50% of the data is to the left or 50% of the data is to the right, the median is right in the middle here. but that is not at the middle of the peak of the distribution. So it's something to keep in mind, again, that skew really does impact these measures of central tendency. All right, so mean. Please, please, please take a note that the mean is very much so influenced by outliers or extreme scores, and it can't, there's no way for you to know just by looking at a number whether it's being influenced by the outliers. That's why you need to be looking at all the scores that were occurring in the distribution set. Anyways, the mean is the summation of all the scores divided by the number of scores. And the benefit for this is that you have stability over time. So the mean doesn't really change that frequency. So that frequently. Woo, too many statistical terms in the brain. But it is very much so influenced by these outliers. And you're going to be seeing that in your homework or your discussion board posting, whatever your class is set up to do this semester. We have some interesting data sets where we take a look at a set with a outlier in it, and then we look at the trimmed mean, which is when we delete the outlier. And then you're going to be able to compare the differences between the measures of central tendency with and without the outlier in the data set. So, something to look forward to, maybe. The median itself is the middle of the distribution. Please underline, star, somehow highlight this idea that it is known as the 50th percentile. This is really important, and especially important to understanding percentiles, that when you're talking about a standard normal distribution, the 50th percentile is the median. That can be really helpful to you in the future. The best thing about the median is that it is not at all influenced by extreme scores, because in general, it's going in an ordered list. Okay, you're the lowest number, you're on one side, you're the highest number, you're on the other side, second to lowest, second to highest. Let me get all the way to the middle, and that's the median. I didn't care about how extremely different these scores were. I ordered them all in a row, and I said, well, these are the low ones, and these are the high ones, and this is the middle. That's it. So that is sometimes why it is a better way of explaining the median of the distribution, and why, if you were taking a look at the summary statistics off of a data sheet, if you saw that your median was was different than your mean by a pretty extreme number, you would be very cautious in what was going on with your data set, because it would probably indicate that you had some outliers in the data. And that's not to say that all outliers are not supposed to be there. Sometimes they are. Sometimes things are just outliers. But in other times, they're mistakes or data imputation that went wrong. And so it's sort of a signal to you to flag, well, what is it about that student's score that's strange, and is it an error on my behalf? Did I mess up somewhere, or is that legitimately their score? So it's sort of a signal flag to us. All right, so the mode is something that occurs the most frequently. It's possible to have multiple modes. It's not that not that uncommon that you would have multiple 84s. So if you had 7 84s in your class, then that's the mode. That's just what happens. There it is. It is the least stable. It's going to depend every single time on the distribution of the data, that it's hardly ever going to be the same. And if it is the same, then there's probably something wrong with the data. But again, it is possible to have multiple modes, and it is not very stable. All right, so when we talk about variability, we start talking about how we have other measures that we think about when we look at data, because we have to have other ways of explaining beyond, mean, median, mode, what's going on in the data set. So the first thing is range. So range is really simple. It's your highest score minus your lowest score. So if you have things ordered, then you know immediately that I'm going 9 minus 3. Highest score minus lowest score, that's your range. That's not really explaining that much insofar as variability goes, but it does get us somewhere. Okay, standard deviation is something that's going to come up a lot. It is the most accurate measure of variability. We generally start any explanation that uses standard deviation with the phrase with a standard deviation of, and then you would fill that in. And you generally report the mean and the standard deviation of something together. And it's frequently an SD or the sigma character, and that's how you may see it. And what it really is trying to get to is how far away from the normal you really are. It's trying to quantify the idea that if you're listening to a weather report and your weatherman predicted that you were going to have rain and it didn't rain, how far away from normal is that? And that's sort of the idea of what you're trying to get at, is with multiple data points, how accurate is whatever it is you're measuring, and how different from normal is it? Okay, so we have seen this before, but in general, again, we're talking about standard deviation. You've got negative standard deviation to the left, positive standard deviation to the right. And if you'll see on the left, it says only 3 points in 1,000 will fall outside the area, 3 standard deviations either side of the center line. And that's really true, and it's something to think about, because you don't see 4 standard deviations all that often. Because if you can take a gander up at the top here, 3 standard deviations out is 99.7% of scores fall in between 3 standard deviations of the mean. You're not going to be seeing 4 standard deviations very frequently, and you're really not going to see anything past that much at all. It's possible, you never want to say it's not possible, but it is really unlikely that you're going to be experiencing that. You're going to probably see frequently 3, 2, 1 standard deviations. That's definitely normal, and or some variation of, so like a 1.7 or something like that is not unusual. But for the sake of this class, we are generally talking in whole number. We're not going to talk to you in decimal places. It's complicated enough. I don't need to add more to it. So we're going to walk through an example now, and it's doggies. This is actually from a fun website called Math is Fun, appropriately named. And so we're walking through this example. You have different heights for these dogs, and they're looking at the heights of the dogs at like the shoulder-esque area. That's how they've labeled how the dogs are tall. So you have this Rottweiler, maybe? That's 600 millimeters, and then forgive me, I think it's a Greyhound, 470. The Dachshund, that's 170. I don't know the name of this dog, but it's 430. And then is that a Bull Terrier? Maybe 300 millimeters. Anyways, the point is not that I know my dog breeds. It's more the fact that you have these different heights. So how would you go about finding the mean? Well, we would add them up. We would say, here are all these numbers. What am I doing? I'm dividing by 5 because there's 5 of them. And that's going to get me to 394. Okay, so when we take a look at 394, that is now that green line that has appeared. That is now the mean of this distribution. So we have, again, these points. We have the 600 ISK, 580 something rather. I've forgotten the numbers already. But anyways, you understand the idea here that you have these different points, and then I have the mean that's running between all these points. Okay, so when we start talking about calculating standard deviation, there's a couple of steps involved. You've got to calculate the variance, which in and of itself has 2 steps. And then you're going to take the square root of the variance to get the standard deviation. Please know that you are not going to need to do this on the exam. You're going to need to understand the principle of what's going on, but I'm not going to ask you to calculate out and take the square root of the variance on an exam. No, because normally if you were doing this in person, you would not have the benefit of calculator, so that would be difficult to do. So when we first start attempting this, we take the difference between the mean and then square it. So we calculate the difference between the means for each individual dog height. So 600 minus 394, 470 minus 394, 170 minus 394, 430 minus 394, blah. Okay, you get the idea, right? So now we're looking at a bunch of differences. You're looking at a difference of 206 millimeters, 76, negative 224. Negative is definitely a possible option here. Okay, so you have these differences occurring. And so the variance is all these numbers squared divided by the number that you are looking at. So 206 squared, on and on and on. You're adding them and divided by 5 because 5 is the amount of dogs we're looking at. So all that boils down to this 21,704, which is a big number. But if you'll remember, this is variance, and we want standard deviation. So we need to square root that. And you're going to get then 147, which is, rounding. But that is the final standard deviation for this problem. So when we take a look, if the green line here running is the mean, positive 147, negative 147, that's plus and minus 1 standard deviation away from the mean. If we were going to go 2 standard deviations, I'd have to add another 147. So that is how we actually go about calculating this. I know it's not an education-based example, but sometimes it's fun. So when we start interpreting this, then we have a standard way of explaining the differences in dog heights. It's a Rottweiler. So Rottweilers are tall dogs and Dachshunds are a bit short, but don't tell them that. They are rather opinionated doggies. So I hope that this example helps cement it. Again, what you're really talking about here is that you're describing the distance away from the mean that these dogs' heights are. So that Rottweiler is more than 1 standard deviation away from the mean, whereas the majority of these are within 1 standard deviation of the mean. So 3 of the dogs are within 1 standard deviation of the mean, and 2 of the dogs, the Rottweiler and the Dachshund, are within 2 standard deviations of the mean, I would say. Okay, so when we start talking about converting scores, you might wonder why. Why do we need to do that? And the answer is not everything is on the same sort of easy to understand mathematical grouping system. So if we have things like a GPA that's got a 4.0 or 5.0, how do we convert that then to our school's version of that? Or how do I convert my classroom test that has a scale of 45 points to a 100 point for the gradebook? And this is where we start thinking about the conversion formula and our raw scores. So these are some terms you really need to be familiar with. We have raw scores and converted scores. Raw score is the actual score on the test. We frequently base these off of 100 just to make our lives easier. But it could be, an 8, or it could be a 16 out of 16. Sometimes we just end up with weird numbers things. Like on one of the projects for this class, we had a maximum score of 42 for one. It was a really strange way we came about getting to 42, but that just happened to be how it worked out. So when we go and convert the score so that we can compare it to other scores on a more familiar baseline, we have to then go through the process of actually changing that score. So, for example, that 42, if I wanted to put that then on a scale of 100, I would have to convert all the scores so that they were applied to each, so that the change was applied to each student's grade to now be on this new scale. So you are welcome to check out more information about this at VARSTATS or VASARSTATS. But in general, we use tools. Frequently, you'll have a dashboard that can do this for you too, which is always nice. But if you don't, they do have free tools on the internet that you can have access to. Okay, so in our example, let's say that our test has 40 items. The mean's 35.69 with a standard deviation of 2.26. If you want to convert it to a 100, you would then say the converted mean is 89 with a standard deviation of 5.65. If you are interested, you can work out the math, and that is how that actually ends up converting. Again, for the exam, I'm not asking you to actually convert the scores numerically, but I want you to understand what is a converted score and what is a raw score. Okay, so when we talk about interpreting standard scores, you have to, again, remember that we have normal distributions. So when we have this normal distribution, we have the ability to break things up into standard deviations. And that is really important to getting back to this sort of standard score. Well, if I can have a standard deviation, then I can then sort of make assumptions and statements about other scores. So when we have a mean and the standard deviation, we can then say that about 2/3 are within 1, 95% within 2, just about everything, but 99% within 3. And what you're saying, and this is important, is that you are somewhat above the middle, significantly above the middle, far away from the mean, or in the other direction, that you are somewhat below the mean, you are significantly below the mean, or you are far below the mean, and the mean being the middle. And that is important because we have some tests that are so preset in their ways that we can make judgments about them without having to actually go and calculate the scores like we had to do for the dog mathematics height example. So these tests, I see z-scores are kind of off the page a little bit. These tests have commonly known means and standard deviations. Like if I went up to someone and asked them what the mean of a z-score is, they're going to know it's 0. They don't need to go and take a look at the data set. The mean of a z-score is always going to be 0 and the standard deviation of 1. Now, you might say, okay, so what? Well, this is really an important thing because when we look at standardized tests, that builds off of this principle. This standard idea is something that our education system is beginning to really appreciate more about comparing students to each other based off of a standardized norm, and how we go about actually getting that standardized norm is important and has to do with these numbers and the way these tests actually work. All right. So this is an example from College Board. This is from their website directly. And it's talking about how you have a raw score that goes to a scaled score so that you're not affected by different versions of the test, because at any given time they're testing out multiple versions of the same test at the same time. So you see the scaled score ultimately. But because your raw score is only what you got correct, and then it's converted, you have to do some equating stuff. And then they give you an example, because the SAT is based on that 1000 score, that you have a 400 okay, so say you got a score of 400 on one day. The way that they have created their equating system and their converting system practically means that a 400 taken on one day is equal to a 400 taken on a different day, even though it's a different form of the test. And that's, in their minds, making it standard, equal, fair, however you want to use that, that to make the test the same for everyone who takes it, even though they're not taking the same exact test. And that's a fairly interesting and fairly strange concept that we could control for all this stuff, to actually then make comparisons between students. And as you probably well know, the SAT is a very strong indication of where you are as a student going into college. Okay, so when we actually calculate these transform scores, you have a lot of things that are going into transforming the scores. You've got the raw score, which is x sub I. You have the mean score, which is x hat, x bar. And I apologize that my bars are so far away from my x's, but it is supposed to be like right on top of it, x bar. X bar is the mean of all scores. You have the standard deviation of x, so the standard deviation of scores. And then you have the standard deviation of, the desired standard deviation of the scores. So this is that sub SS, and that's to denote that this is desired. You want this. Okay. So the formula itself looks like this. I've kind of flagged them. I see that it's kind of strange to twerk your neck to read it like this. So you're adding the desired mean to this bracketed statement. So you're taking, initially what you're taking is the raw score and subtracting it from the mean of all scores. So you do that, you divide it by the standard deviation of all scores, you multiply that by the desired standard deviation, and then you add the desired mean to it. And that's kind of a messy way to transform a score, but it is the formula that works. And no, you do not need to know that for your exam. You don't have to memorize it. But it is helpful to know as you go about doing stuff like this, that this is how this actually gets there. All right, so this is an example worked through. I am not going to read every part of it to you, but in essence, you're plugging in the raw score, exactly the way the formula works, and this is for calculating a t-score. And so you get all the way down there and you get that 65, right? All right, so then in this page, you're doing it again. You're taking the student score of the 90, the mean, 75, subtracting the student score from the mean, dividing it by the standard deviation, and then working your way down to a 122.5. And that's the standard score. All right, so when we, again, talk about all these things, we start being able, because they're standardized, to make statements about T-scores, deviation IQ, stay nines, and in the future we're going to be talking about percentiles. But all of these because of the way these distributions work, we're able to make statements about what things are above average, or above the mean, or below the mean, or they're within one standard deviation of the mean. Therefore, that's about 2/3 of the scores are within one standard deviation of the mean. So all of these things are descriptive explanations for things that you're going to be seeing in your near future as you work in education, where we describe test scores using these terms. We say that, how is my student doing? Oh, well, she's doing above the mean, or she's doing, somewhat above the mean. She's doing pretty well in her class. Or conversely, well, they're somewhat below the mean, or he's significantly below the mean, in which case you might need to be seeking help. But that this is, important in our way of communicating these results without getting ourselves in trouble. All right. Please let me know if you have any questions. My contact information for Dr. Turner's class is on your board, and my class, you know how to contact me. All right. I hope that this helps you, and that you are less confused going into it, or that it was a review and that your understanding of it is on par with my own. And I appreciate you hanging with me, going through all this information, and I'll see you in percentiles shortly. Bye.